So we are very pleased to have today with us in our Bar Ilan University Vision Science Seminar, Dr. Nir, with an R, Shalev from the University of Haifa, and I do apologize for the mistake I made in the invitation sent. Nir Shalev did his BA in the most prestigious program in Tel Aviv University, if not one of the most prestigious ones in Israel, Adi Lautman's interdisciplinary program for outstanding students. He then did 2 concurrent MAs at Tel Aviv University, one in special education and learning disabilities, and one in cognitive psychology. These were followed by a PhD in experimental psychology at the University of Oxford under the supervision of the renowned Professor Glyn Humphreys and Professor Nell Demier. I hope I'm pronouncing this name correctly. And this was done in the Cognitive Neuropsychology Center. He did his postdoc at Professor Kia Nobre's Brain and Cognition Lab at the Oxford Center of Human Brain Activity in the University of Oxford. He then became a junior research fellow at Wolfson College, and he then was appointed a departmental lecturer in experimental psychology and a college tutor at St. Hugh's College and Jesus College in the University of Oxford. Last year, he joined the University of Haifa as a faculty member at the Department of Gerontology, and he's also affiliated with the Institute of Information Processing and Decision Making and the Haifa Brain and Behavior Hub. He received multiple awards, honors, and fellowships as the accredited fellow of the Academy of Higher Education in the UK, Commendation for Excellence in Teaching at Oxford, Dean's Academic Excellence Scholarship at Tel Aviv, and a Marie Curie Fellowship. Dr. Shalev has an impressive publication list that includes top journals as Psych Science, JEP General, Trends in Neuroscience, Trends in Cognitive Science, Nature Reviews Psychology, and others. He's interested in development and aging, and his research focuses on attention. He investigates how attention changes with age, with various brain pathologies and behavior syndromes. His work also covers other aspects of higher order cognition, such as memory, inhibitory control, and anticipatory behavior. And today, we want to welcome you, Nir, to our seminar to tell us about your interesting research, and we're delighted that it was possible for you to join us. Thank you.
Thank you, Sharon. I'm very excited to be here, and thank you so much for inviting me. As Sharon said, I'm Nir, and I'm going to talk about dynamic guidance of attention across the lifespan. I will, of course, acknowledge the people who worked with me as I speak, but I would like to start with a huge acknowledgement to Sage Botcher from Oxford and Kia Nobre from Yale. The two of them are involved in everything I'm going to present today, including some of the figures and some of the illustrations. So just saying it now, so it will be clear throughout. Otherwise, as I said, I'm very glad to be here, and I feel like I got the perfect introduction 2 weeks ago in a talk given here by Professor Sarah Schomstein, who talked about guidance, essentially, and how there are many, many factors that determine where we attend. And this is something that I also ask questions about, but here I'm trying to make a transition to asking about guiding attention in dynamic scenes. So when we encounter scenarios that are changing and how we adapt and change in this kind of contexts. So I'll go back to the talk from 2 weeks ago. After a very short introduction, just setting common ground, I think I'm not going to say anything very controversial in the next few slides, at least. So we're talking about visual search, the kind of a task that is normally used to study attention prioritization of signals. So, for example, here I'm taking you all the way to this peaceful part of I think it is near Iceland. It was taken by Sage, by the way, and the task is to look for dolphins. because dolphins are cute. And we are trying to find the dolphin's fin. I can help you. Can you see my mouse pointer, by the way? Just, okay, yeah. So the dolphin's fin is here. And this is a search task because it's a very rich environment and you kind of need to move your attention here. And what most people will agree is that we have this tendency to be attracted by salient signals at the beginning. So these beautiful sparks here on the water will capture our attention because they are salient. But this is not our main task, right? Our main task is to find dolphins. So here comes the more mature, responsible attention guidance, which is related to our current goals. Right? So in that case, we're looking for the fin, and we may have some information or prior idea about what the fin looks like, or we may look for darker shades here. But the point is that we have a goal in mind, and we use this goal to optimize attention and narrow down where we're looking at. Now, these are the big ones that we've been talking about for decades, or other people have been talking about for decades. But there's, of course, this new stream that is constantly growing that gives a lot of attention to the role of experience. So the idea is that while we have those bottom-up, top-down signals, this goal-driven and stimulus-driven attention, we understand that our experience is also a very meaningful factor in what we attend. So generally speaking, experience cannot be limited to any time window. It can be very long-term experience, such as our long-term knowledge about the configuration of a scene, or in that case, if you're looking for dolphins, it is very likely that most neurotypical observers will focus around here when they look for dolphins and are not going to look somewhere in the mountains for dolphins. It's very important because it can really help us narrow down the search region, for example, and that's just one way in which the scene rules, grammar affect the way we are searching in realistic scenes. And of course, there is the more short-term experience that can shape our attentional guidance. You can talk about contextual cueing, the way we store the general configuration of the visual scene, telling us where we should look now. And there's a whole family of what people call selection history. So places we found targets earlier may affect where we search now, and so on. The point so far is that experience shapes our behavior, and I'm quoting here the talk from 2 weeks ago, talking about platypus. The idea here is, and I think philosophically it's very interesting, the point that was made that we are constantly finding more and more sources of guidance, and we are saying, okay, they cannot be categorized, okay? So gradually they fall under this umbrella perhaps of the experience, because we're talking about semantics and affordances and size and its role in a visual scene, and emotions and rewards and so on. And they are related to us being human and accumulating knowledge and understanding of the world in a way that will, in the end, bias our visual attention. So that was the textbook introduction so far. Moving onwards, I would like to put in bold this sentence, the idea that experience at multiple timescales continuously will shape our behavior, the way we guide attention. And it raises a question, just to provoke our minds here, I would say, how well can we actually understand a dynamic system using static stimuli? And because we learned a lot about how we guide spatial attention, but of course, time cannot really be separated from space. And I'm keeping some ambiguity here when I say dynamic system, because everything is dynamic. The external world is dynamic, things change, and of course we change, right? We accumulate information about the current scene, but also we mature, we develop, and we may change the way we allocate attention based on what is most important to us when we are 4 years old, when we are 12 years old, when we are 20, or when we are 70 or 80. So everything is a constant change. And you can say it is in the foundation of Western philosophy. This is a Heraclitus say, no man ever steps in the same river twice. for it is not the same river, and he is not the same man. So the external reality changes, and we change. So everything changes all the time. The environment changes. Natural scenes are dynamic, and we have to account for it when we consider spatial attention. Our cognition changes as we gather experience and we learn about rules of the scenes or rules of statistical regularities, and we continuously develop. So we have to kind of ask ourselves how we can move onward from this snapshot of reality that we are normally taking in spatial visual attention, and talk about things that are changing. In real life, time and space cannot be separated, and they are integral to our perception. So let's go back to this search example, and again, crediting the video to Sage. I've never been in such a scene, but this what a dolphin, I almost said hunting, but dolphin, looking at dolphin looks like, right? So you have, I don't know, my video here is a bit jumpy, but believe me, it's a highly dynamic scene, and you have dolphins coming in and out of the visual scene over time. And the point is that if I'm looking for dolphins here, sometimes they will appear on the left side, sometimes they will appear on the right side over time. But I'm there also, and I can gradually pick up rules about their behavior and learn when and where to attend. So when the dolphin on the right will appear, when the dolphin on the left will appear, is based on some sort of a set of rules that I can probably extract just by being in this dynamic scene. There are certain regularities that can help us guide performance and help us optimize how we attend. And this is the kind of experimental design I've been looking at. And I should say it is not something that is only relevant to this niche of dolphin, again, not hunting, dolphin observing, okay? It is, us as drivers, we are experts in knowing when is the right time to look where, right? It is something that we have to do, actually. You can think about yourself deciding even, God forbid, when to check your WhatsApp notifications while driving. That's because you are an expert in knowing, well, we are normally statistically think we know when that we can take our eyes off the road. Or perhaps if we're now standing in a traffic light and we know that the traffic changed to red, we have enough time to do something else. And once a school teacher told me that children are really good at that as well, right? So sitting in a classroom and knowing when is the right time to attend your notebook and to take comments, and when you need to attend again the blackboard in order to focus your resources there. And the impossible task of leaving a bus, right? Even knowing how to actually get off a bus. It means that you need to time yourself very well when and where to attend. When is the right time to start pack your things? When is the right time to press here? When is the right time to get up? In all these tasks, they are highly dynamic and they take spatial attention over time. So in today's talk, I'm going to look into dynamics from two perspectives. The first part, which will be now, is how people use spatial temporal regularities to guide attention when the environment is dynamic and changing. I will then talk about the lifespan developmental aspect of it. So here's a question that we can address empirically clearly. Okay, so people learning when and where to attend in dynamic scene. This is the experimental design that we presented in our JP paper in 22 with Kian Nobre, Sage Watcher, and Jeremy Wolf. We had 4 groups of 25 participants each, all with a power that was predetermined to be over 0.9. And the task is a visual search, but it is a visual search in a dynamic visual search. So this is what a single trial looks like. We're telling people you need to find 8 targets, and a trial will last about 12 to 13 seconds. This is the search. Look at the mouse pointer here. Okay, well, Here it's a bit, again, it's not very smooth, but whatever. So you see that targets come fading in and out of the display over time. I don't know if you really get the sense of how dynamic it is, so trust me. What you see here is that the items fade in very gradually over about a second and a half, then stay on the screen for another second, and then disappear again very gradually, and there's noise there in the background. And they need to ignore tilted lines and only attend vertical bars that appear on the screen, okay? So you have 8 targets fading out very gradually among visual distractors that also appear very gradually. But, and that's the point here about the learning and predictions, just like in real life, some of the items we're looking at, they have some sort of a pattern that can be learned and can be extracted. So what we do here is 4 out of those 8 targets that actually appear predictably. It is a bit like a statistical learning task, only that the predictions are not 100% valid in space. Instead, let's say participant A will always see a target that will appear somewhere in this spatial quadrant here in the bottom left side, okay? It will always appear there throughout the experiment about 2 seconds after the trial began, okay? So you can learn a rule that you need to search here for a target, let's say 2 seconds after the trial begins, and then there will be a target somewhere here after, let's say, 5 seconds, always within this spatial quadrant. And here, let's say after 6 seconds, and here 9 seconds. And because we had so many variations of the task, I always start by saying, let's say, because we had lots of different versions of this experimental design. But in principle, people been seeing randomized versions of and different rules here. But it is the same principle. You can learn to predict the approximate location or special region of something at the exact time throughout the experiment, okay? So we said we had 8 targets, but 4 targets were predictable, 4 other targets were unpredictable, were random. So they could appear at any time in any location. And here again, let me add some reservation. We had so many different variations of this task that we also played a lot with the statistics here that are not very simple actually to control for all the factors. But in this JP paper, we had 4 different experiments, for example, looking at those distributions and so on. So random targets are important to us because they provide a good baseline of how you act when there are random things compared to predictable things, but also they allow us to eliminate any sequential learning, which is critical here. It is really about time. And when I say it is really about time, let's take, just for this example, there is a target that will always appear at the upper right quadrant after 5 seconds. Okay, and you can see here with this clock, it always appears at the same time. But if you look at the sequence of targets, you cannot guarantee it will always appear as the second target or the third target or the fourth target or the fifth target, because we use the random targets to break the sequential learning. So it is not that you can just learn, let's do left, right, bottom, left, right, right, because there's no rules of this kind that can help you. You have to somehow bind the timing of events to their spatial location. Let's look at the data. So I'm going to show you now the comparison of inaccuracy first between predictable and unpredictable targets. So most people find more predictable targets compared to unpredictable targets. And again, out of 4 experiments in this particular paper, we had about 90% of our participants showing the same pattern in accuracy. Another thing that we need to verify, at least in this stage of validation, is that those accuracy differences are not driven by just remembering the first target will appear here and the rest is the same to me. So really looking at learning at this very extended time. So what I can do, for example, is to look at the accuracy, how well you find those third targets out of the predictable ones compared to the average third target from the non-predictable ones. And you can see that those biases, if you want, or those benefits appear throughout the experiment. So even 10 seconds into the experiment, people can still represent that a target is likely to appear at the upper right corner, for example. We don't only see it in accuracy, we also see it in reaction times. Here the effects reach the time window of 100 to 200 milliseconds difference for some participants in finding predictable versus unpredictable targets. So this was so far the behavioral observation. People are better, and we replicated this finding many times. We can now say, well, this is a highly dynamic task that extends over time. So another thing we can learn about predictions is by looking at dynamic markers of behavior. I'm going to show you data based on tracking people's mouse movements, eye movements, and in the end also those clicks that represent the reaction times, of course, and the accuracy. So again, it is the same, pretty much the same experimental design with a small change. The study I'm presenting now is something that I did together with Ayelet Landau and Kian Obre. Danielle Filmon and Non Sionit are two students at the Hebrew University, and Sage Butcher, who's involved in all this research throughout. And here we asked people to do it while tracking their eyes and hands, but also we added a manipulation of altering the distraction load. So this is just another flavor to our experimental design, also seeing whether predictions are affected by just changing the amount of noise you need to ignore between trials. So participants always seen the same regularities. Let's say they always had a target down here after 3 seconds at the bottom left, but this target appeared among low distraction load or high distraction load. And it's another perspective of the learning here to see whether there's an interaction between the distraction and predictions. I can already tell you that there's nothing. I mean, it's just completely orthogonal, these two effects. I'm going to show data here based on 37 participants after cleaning some people with problematic eye movements data. And we have these two conditions, the predictable versus random targets and the high versus low load of distractions. Let's look at behavior. We can see behavioral benefits that happen here. So people find more predictable targets compared to random ones, irrespective of the competition, irrespective of how many distractors. There is also a main effect of distractors. This is your search slope, if you want. Okay, so adding more distractors leads to you finding fewer targets, but they are independent. We also see increase in variability of responses between the conditions. So again, two main effects. You have higher variability for unpredictable targets and higher variability when you increase the number of distractors. And in reaction times, we only found here predictability main effect. Okay, so people are faster, but distractors go in a similar direction if you look at the data. But these two effects are independent, meaning that looking at dynamic markers now onward, I'm just going to collapse across the two conditions of distraction. I'm not going to look at it anymore. So let's look at the pattern of eye movement. There are different ways of looking at these data. Here I'm going to baseline it to 0, to where your eyes were at before moving, at the moment of the target onset. And let me remind you that the target starts at 0, but it is fully visible at around 1.5 seconds. So it takes time until it actually appears on the screen and people can fully see it, and it appears on overlaid on noise. So this would be the pattern of eye movement that, in that case, I'm plotting you what happened when you predicted a target. And I can do a similar plot for unpredictable targets. I'm adding here a few hallmarks for you. Red is the mean RT for predictable target. Black is the mean RT for unpredictable targets. So you can see the eye movements happen before. It should not surprise you that it doesn't reach 0 because we are baselining it to the onset of target. So there's a bit of smearing of the signals by plotting it this way. And you have the moment of target onset when it is fully visible. That's actually when it reaches the peak or the trough of this signal, when it starts fading out. So the reaction time is somewhere between the moment it reaches full visibility and the time that people actually select the target. And we can run a statistical comparison to see that the two lines are not the same, at least at this point. So what I'm seeing here is a result of people getting closer. I can show it later in a different way, but these two lines are slightly different already at this very early stage, way before the mean reaction time. So before it reaches full visibility at around 800 milliseconds, we already see the two signals depart, meaning that there's some sort of different eye movement pattern towards predictable targets. And I think actually the mouse is even clearer to see. So this is the pattern of mouse movement toward predictable targets. And look how it compares to the mouse movement towards unpredictable targets. Okay, so also here there's a clear statistical difference between the two signals. So people move closer to targets actually in this condition. I'm going to delve into two, I think, kind of interesting task markers based on what you've seen now. First, look at learning. So obviously there is a strong learning element here because people form predictions, meaning that they learned. And what we see in this task is that over time, people actually start relying more and more on predictions. In order to do so, we can just calculate the mean reaction time for predictable and unpredictable targets at each block. We can subtract the two to extract some sort of pattern of learning, and you can see it becomes more and more dominant. When eventually it goes in average more than 100 milliseconds difference between finding predictable targets versus unpredictable targets. Okay, this is something that can be tested statistically, and we can see that there's a clear effect of learning. Interestingly, when we look at mouse movements, we can also find the same idea that if we test in block 1 the difference in pattern of mouse movement towards the target versus block 5, you can see the differentiation between the two lines much better in block number 5 compared to block number 1. So wherever you see here the gray color means that this is statistically different, and you can see that people start showing those the differentiation between the two signals much earlier in block 5. So as you learn, as you continuously engage with the task, you gradually start moving your hand earlier towards the target that you can predict. And I hope it is very clear here that the two signals are clearly distinguishable. It happens not only in mouse movements, but also in eye movements. Look at the difference here between block 1, where essentially the two lines look the same. So the pattern of eye movement for the two conditions look the same in the first block, and in the last block, the two conditions are very different. Okay, so you can see a clear difference in how close they get and also their distance. So you start moving your eyes earlier towards the target, only towards, let's say, in block 5 compared to block 1. We also find another pattern that I think is super interesting, which is that predictions increase the precision of your behavior. So it is not only that you learn to predict. You know, many people look at those standard deviation of reaction times, or you can divide it in reaction times to make it maybe a more valid measurements. But in principle, variability in responses increase for targets that you cannot predict. That's something you see in reaction times. We also look at mouse movements, and here we are looking at 0 point as the baseline, and we find that there's a difference also in how close you get to the target with your mouse when you can predict it. We can see that also people move their eyes closer to the center of the target when it is predictable, and you can characterize it by creating these maps of clicks around the target. So if you imagine that this is the target and these are just individual pixels, we can measure the probability of clicks at each point here, and we can compare those distributions for predictable versus unpredictable targets. And we see that people click closer to the center of the target just because it was predictable. So it's not only that they're faster, something happens to your overall precision. You get closer to the target with your mouse, you get closer to the target with your eyes, and you click closer to the center of the target when it is predictable. So what we know so far? We can see that spatial temporal regularities are an important factor in guidance of visual attention when we start introducing dynamics. So when we open up this opportunity for things to change, we see that people pick up on regularities and use it to optimize spatial attention over time. We can see that learning is reflected in changes to those motor trajectories of eye movements and mouse movements, and we can see that it does something to precision. I would like to point out that I see lots of very, very interesting works along these lines over the last few years. And there are other people that probably should be acknowledged, and I'm sorry for missing it, but some interesting work about how people prepare in time for the appearance of visual stimuli and use time in order to optimize spatial performance, and also tasks that contain a bit more rhythmic structures, but also over space, can also shape the way we guide spatial attention. The main point is that this proactive prediction-led guidance of attention is something that we see again and again in different designs once we introduce the idea of dynamics, once we allow people to combine time and space in a spatial task. And now maybe the side that I find most interesting, and I've been looking at quite a lot recently, and that's the idea of how it develops. So let's take a step back, zoom out to talk about attention development. Again, we are going to take the textbook version of what we think about visual search development. Okay, so normally what people like doing in comparative developmental research, they would plot this imaginary axis of performance here on the Y and age here on the x-axis, and we'll say, well, let's see how well you do something. Okay, so we have, for example, experiments that involve saliency-driven, stimulus-driven attention, and you can start measuring how people at different ages are attracted to salient stimuli. This is a bit controversial, what I'm going to say now, but children are overall, we believe that children are born with the ability to be attracted to salient information. We think it is a main driver of your behavior in early stages of development. There are quite a lot of works on it. But also children develop their senses, so they're not at a perfect abilities when they are born, but they have something. Okay, so even at a very early stage, even with infants, you can use different noises and different manipulations of pop-out search and so on to look at human development and demonstrate the effects of saliency. There's a bump in early stages of development. This bump is somehow attenuated, but still growing until brain maturation, which is this very abstract age group of 20 to 30 years old, but very difficult to characterize. There's a plateau, and then characteristically, and I'm just going to say something about it, it's not always true. Characteristically, there is a decline, and this decline is not because older adults don't use bottom-up attention. It is related to the fact that there's increased noise and sometimes a degradation of perceptual abilities that make people sometimes less sensitive to stimulus-driven attraction of attention, right? Because if you, we talked about it before the presentation began, but if you don't hear very well, and I'm going to use an alarm to attract your attention, it may take you longer to respond to it. And I suppose also the point of attentional decrease in processing speed, for example, will also affect somehow the increase in noise in your system that will affect perception. I've seen some weird notifications here, but I couldn't make anything out of them. Everything okay? Sharon? Yeah?
I don't know.
Okay.
Yoram is actually, I don't know if it's part of the show. He's changing the background of the display, which, I mean, I know he's the host, but this has never happened to me. So Yoram, if you hear me, please
sorry, I wasn't
stop.
aware that it's
well, I'm just seeing my presentation slides.
No, it's
Okay,
exactly,
I'll
who
try
is
to
noticing
find,
this. I mean, it matches, it corresponds to what Nir is talking about, but still.
The topic, yeah.
Okay, you can just
Yeah.
Okay, leave it. Yeah.
So this will be the salience kind of driven attention. Early sensory development enhances the effect of saliency, but also declining perceptual abilities will somehow increase the noise and will make people overall decline. And there's a mirror image to it with not really mirror image, only in early stages of the goal-driven attention, which we believe people don't have at the very early stages of development. It develops very slowly, but then there's a bump all the way to this abstract a maturation of the brain that declines alongside normally the declining working memory abilities, potentially making just a little bit more difficult to hold a goal, a fixed goal in mind. So again, there is this gradual maturation of frontal lobe functions that increase goal-driven attention, but also there is a declining in those aspects of behavior, even though you should have some reservations. And it creates this average line that we see again and again, very stereotypical. As someone in a gerontology department, I'm concerned about these kind of figures. This is extremely stereotypical presentation of aging in general. But in principle, you will see it again and again, this inverted U-shape of human performance. And if you measure people performing search, you will get the same thing. So normally in the traditional static visual search, children are not very good, older adults are not very good, everyone wants to be 20 years old, and that's it, right? So we move now to the same experimental design I presented earlier, now trying to ask this question in the context of development, and I can run faster because you know what the design looks like, so we can focus on the findings here. So first I'm going to look at children comparing, I wanted to say comparing Sage, Kia, and Sage. No, Sage, Kia, and Gaia contributed to this work published in Child Development. We are asking questions about children here. So we're looking at this stage of development where normally children are not as good as young adults. Taking children at 5 years old, 5 to 6 years old children, comparing them to 20 years old would normally yield differences in search performance. But the question here is, what about their ability to learn and use those repeated regularities that are embedded in the task in order to optimize behavior? So what happens when we also add to this kind of shape the idea of learning-driven attention? And you've seen the task design before, right? But this time we are asking them to use a tablet and click on airplanes and ignore I think, shapes of birds and butterflies. So it was kind of more gamified version. This is Frick Van Eed's daughter doing the task. So I'm just going to show you from the back what it looks like. Okay, you see how she, and you don't see because it's videos are not great. But this is what the task looks like. We tested 80 children in a school in London. These are the results. Okay. Young adults in their 20s are much better than young children in performing visual search. The overall accuracy is clearly different. But if we look at predictions, we see no difference. There's no interaction here. There's just one main effect, that participants are simply better at finding things they can predict irrespective of their age. So predictions-led behavior is present already when we test children who are 5 years old, and look at those massive differences in overall performance. So while children find in average, young adults find 95% and children find below 80%, they still have the same ability to extract those regularities and use them in a goal-driven manner. This effect it means that age is likely to be related to overall search performance, but not to the basic ability of forming predictions. We could actually see it within this age group. Okay, so what we can do is create the average performance. This will be your search abilities, I don't know, top-down attention, whatever you want to call it. And you can look at prediction benefits. So the difference between the two conditions, whether you find more predictable or more unpredictable targets. And because we had 80 children, we can look at the correlation between age and these task markers. And again, you can see here that the x-axis here it's a single age group between 60 months to 70 months. It should be very concerning to parents, I suppose, or to educators, that within a single year, we can record significant differences in the overall ability of performing a visual search. And it links with age. So the older you are in the search group, within 1 year, you will find more targets. And it goes alongside with the idea that we develop this top-down guided search. But if you look at predictions, it had nothing to do with age. let's take it a step forward to a paper that we recently published with Sage and Kia, looking at adults. So now we're sampling a broad age range between age 20 to 80. We test them at a slightly, I mean, it's the same task. It looks like this this time. So people are searching for triangles and ignore that point upward and ignore triangles pointing downward, but it's the same search design. And we all know how to look at the figures, so let's jump to it straight. What happens to mean performance as a function of age between 20 to 80? Not a huge surprise. Older people find fewer targets. For those of you who are interested in aging, I should emphasize that this particular 80-year-old performed better than the average 20-year-old. So there's always room to consider variability, and it could potentially be even more interesting to ask questions about variability in aging. But overall, when you compare people in this equal distribution of 300 people between age 20 to 80, we find a very clear trend of declining performance. But what about learning? So again, we can use the same outlet to plot the data. We can say that people here around 0 formed no predictions, that people I mark in red, they found more predictable targets, for example, compared to unpredictable targets, and in gray will be the opposite. And these are the data. So if you look at the trend line, which is well above 0, it is not negative at all. If anything, then it is positive. I would say not significantly, but it is not negative, not implying to any negativity. So learning sustains throughout development here. And what changes is the overall accuracy. So we see a reduction in performance over time alongside a very stable ability to form predictions in 5 years old and in 80 years old. And so I'm starting to wrap up. I think that's probably appropriate now.
As you please.
Okay. So some bigger picture points I'd like to make. Dynamic scenes lead to the dynamic updating of spatial priorities. And I really liked it I'm complimenting again to this brilliant talk by Sarah Schomstein 2 weeks ago, but because she mentioned it, it really fits some things I've been thinking about, and not necessarily putting together in the same way, but that we must consider a way to ask ourselves how we update spatial priorities. Obviously, they need to be updated all the time. And the question whether there is a pacemaker behind the stages, right? Whether we are capable of attaching to it some sort of clock, something that looks like this, right? I've seen a dolphin here, and I think this dolphin appears I see it coming out of the water every few seconds. So I'm forming a spatial prediction that is bound to some sort of internal clock. And this is the kind of big theoretical question that needs to be refined, I suppose. But from a developmental perspective, you can say that, I mean, maybe not from the very early stages of development, but we see that this ability to form those predictions, to gather experience and to use it in order to guide attention better, as based on timing or based on semantics. That's not really my field, but it looks like it's something that remains throughout development, right? So young people probably are not going to look for dolphins flying in the sky, but also young people apparently can learn very well about the timing and locations of visual targets. And similarly with 80-year-olds here. So really nothing happens to this ability in terms of human development. It sustains. And it brings, an interesting question about human development, because for developmentalists of lifespan, there are things we like to say about, for example, kids being very attracted to salient signals in their environment. Because, I don't know, we have all these big theories about how, a bit clunky here with those videos. We believe that children, in order for them to learn better about the world, in order for them to be explorative of their environment, are attracted to salient signals, and they are very stimulus driven. And we think it is adaptive. Okay, and we also think that as we mature, we become more responsible, caregiving, and so on. And we need to be, and we are better or more likely to rely on the current working memory representations that as we perform a visual search. And I think a nice contrast here is to think about yourself crossing the pedestrian and think about a child, 5-year-old, and a 5-year-old may notice something super interesting in the middle of the road as you cross. And that's why it's very dangerous for them to cross the road. However, neurotypical young adults will be very good at crossing a road, but may not notice this very interesting thing on the floor. But we don't never stop developing. And it could be an interesting angle about aging that, as we age and potentially because, we cannot rely on our senses as well. And potentially our memory also declines a bit. It gives more space to reliance on experience and long-term understanding of the world. And it could be, people like to call it compensation. I don't even think it's a compensation. I think it sounds to me very adaptive developmental trajectory of attention that gradually, as you pick up more experience and you have, better predictions about how things should look like, you can gradually rely more on those predictions and less on the online working memory abilities or perceptual abilities. It really raises a question how sensible it is to compare everything to this perfect mind of a 20-year adult. My last slide here is something I often tell clinicians. I teach a lot of clinicians in the program here and say, in a way, how we measure cognition. This is a cognitive task that is used to measure cognition in a very general sense. It's called the MOCA. What we normally do is try to introduce surprise. We try to see how the system operates under conditions where it cannot rely on prior knowledge. We create random lists of words, we create random settings of spatial configurations and so on in order to assess this immediate online cognition. And I think it's interesting because at the same time, the strength in aging is relying on experience, right? So in most the places where people mature and do things better is where they are allowed to accumulate experience. This is why we believe that Supreme Court judges are better when they are 70 and not when they are 25. And this is what we back then when we had in Israel Supreme Court judges. No, sorry. Or this is why you would rarely see a orchestra conductor reaching their peak when they are 35, because because there's lots of knowledge here to accumulate that really shapes also the way you will react to the external environment. So there is a reason to believe that adaptively healthy cognition will rely a lot on experience, whereas the way we measure and think about healthy cognition is only through coping with novelty. So that was my kind of a take-home point that I wanted to make. I would like to make a few acknowledgements. So of course, the Ma'amaka IIPDM in Haifa, where my lab is based, and the Faculty of Social Welfare and Health Sciences, Department of Gerontology in Haifa. Also, the Israeli Science Foundation, Wolfson College at Oxford, and the Academy of Medical Sciences, all funding bodies that supported me. And of course, huge thank you to you and always to Sage and Kia, who are involved in everything I'm presenting here. And that's it. I have to take questions now. No, yeah, I have time to question.
Neil, thank you very, very much. This was such an exciting and really mind-opening talk. And I want to ask everybody to unmute yourself, and let's first give Neil a big applaud. Really great talk. And of course, I have a few questions. Yes, so if you're happy to take questions, we'll be happy to. I'm sure there will be people who would be happy to ask. But first, I want to say something really interesting about the last point that you said. And I must, I never mentioned my grandfather, but here I go. So he actually always said, when he was alive, that he would have liked to be born in his mental, like an old person, and switch the trajectories between his body and mind. To have the capacity of an old person in a young child's body. Yeah, that's
Yeah.
one thing. And another thing I wanted to say about the learning, what you said, basically, it looks to me, I mean, it resembles to me the vocabulary, as if you, children learn vocabulary, language structure. They don't have the vocabulary, but the structure, they learn it really fast. And then they can, they don't have a big, so they may not have the word, but when they're young, they're able to pick up, these rules. And it seems that this is what you're seeing. Okay, now, and here I go with my first question. Whether you think that you found, the issue that you're saying about the deterioration of the older adults with that you saw mean reduction, not in the learning, but actually the mean was reduced. Do you think this has to do, I mean, did you examine the possibility that this is due to reduction in contrast sensitivity? Because there's, you've got gray, the contrast is, adults see that really much worse. I mean, the contrast is reduced across age. I'm just, wondering what would have happened if you would have done that on, well, I'm sure the task would be too easy if you would do it on a white background or a black background. I'm just wondering what
No,
do you
not
think?
necessarily. And I think it is something that I would really like to do to actually it is on my grant. I still didn't do it.
Oh,
But
okay.
but I think but it means, of course, that I was also thinking about it. This task is very slow. It is very slow. People find the targets. It is not necessarily or they can see the targets. It's not necessarily the bottleneck, but, and there's a huge but here. I think so far I allow myself to play with these two factors, right? We say bottom up, top down, right? So it is not unlikely that some of the decline here can be attributed to reduction in sensory abilities. I would imagine it is. I think in general, it is very easy to pick up on the classic traditional literature of visual search and say, oh, the older you are, you're not as good in finding targets. And huge researchers been looking into the factors that will dictate how worse you'll do it, right? So you have huge works by Trick and Enns, Hommel, Madden. There are some, I may be mispronouncing some of the names here, but big figures in lifespan development that that looked into these bottom-up, top-down factors. To me, I allow them to blend here. I think the best way to test it would be starting with by equating the contrast or the maximum contrast of those targets, and then just running the task again. What I anticipate is that we will still find differences because in the end, it is there are some hypotheses about aging saying that nothing happens to your executive functions or working memory or goal-driven behavior. It's interesting, but I'm not sure it is always just sensory. I think it looks like, in general, when we measure working memory, for example, in older adults, we find a reduction in working memory. So, and to me, working memory and goal-driven attention, they are closely related. I mean, in that case, you have to hold a target in your mind and kind of match it. So I anticipate I could attenuate those age-related differences, while at the same time, it will have a meaningful effect. What I will be very interested to see is whether it affects learning, because I would say that a very bold speculation is that if you equate the sensation, you may discover that older adults learn better. Because now when you equate the field, then they will have more benefits compared to younger adults. And I think this will be a very interesting prediction to make and to test.
Or maybe they have, bigger, higher motivation
Yeah, because
to
they don't feel like things
succeed.
that are missed. Yeah.
I don't know,
Yeah, sure.
maybe, or young people are, let's just do it and go. And they are, maybe I'm wrong, but yeah, really interesting. Great. Okay, so I've got more questions, but, I'll let others ask. Okay, so I continue. So I've got another one, and I wanted to ask if you, when you did, when you looked at the eye movements and the mouth, which is just, beautiful, to be honest. So I want to ask if, and you see the learning, but I wonder if you see that there are, if you looked at the deltas between, I mean, you showed the mean
Yeah.
between, but have the deltas shrunk, and have they shrunk in a different manner between the predictable and the non-predictable? Because you would assume that maybe, for the predictable, yeah, I don't know if I'm explaining myself correctly, but, across the blocks, would you get improvements I mean, would the difference or the delta between the eye and the hand
I see what you mean. Yeah.
stay fixed because this is let's
Yeah.
say,
So
personal trait, or would that also influence something, in the synchrony between the eyes and the hand coordination?
I will be adventurous in my reply here, because I think there is something there to still figure out. What we've seen, and again, this is just an observation, okay? So I'm not making a strong statement here, scientific, is that in our data, in more than one experiment, eye movements are much slower to learn. So it sounds a bit strange, but if you look at the first block, it is almost as if you're not yet programming your eye movements to look earlier towards the targets. It is something we've seen in different settings, labs, and eye movement recorders. So one in the study that I presented with Wolf, Nobre, and Botcher. The other one is the one I did now with Ayelet Landau. In both cases, the eye movements took longer to be convinced, if that makes sense, as if, and of course, we are allowing free eye movements here, and that's something that should be controlled in the future. So we may want to even see whether the learning at the beginning, so here's the speculation. The speculation is that you start actually with very coverts, with covert shifts of attention that are led by your predictions, okay? So at the beginning, you form this model of predictions, but it is a bit wasteful and perhaps risky for you to also move your eyes this way. So you start by attention that doesn't really lead eye movements that fast. But I suppose after 5 blocks of seeing the same regularities, you are completely entrained to this structure. Whereas in mouse movements, it's more about the actual clicks, and obviously wherever you will see reaction time differences, you will see in the end a difference between those clicks. So this is why we also looked at those markers of where you click, but this is not something that is presented here as developing over time. So the trajectory of mouse movements is very clear, very fast. The eye movements are slower. And we've seen it in multiple studies, but because it wasn't the focus of what we looked at so far, it's not. I'm not making any strong statement about it.
Yeah, really interesting. By the way, the fact that they're making, I mean, let's say they're using covert attention, could be because, if they move their eyes, they have a loss. They could be missing a target, during these, saccades across. So actually leaving, let's say, I don't know if they actually maintain more or less central screen vision, but if they have, it's, sorry, I'm yeah, I've got
I promise you'll be coughing.
yeah. They have some better coverage, spatial temporal coverage of the field without, some blind fields, temporal blind fields, let's say, when they make these, when they start, jittering their eyes across space. So it's actually, I mean, I would assume it's, if you try to build a model, I would assume this may even be the one that would be winning, the most effective.
Yeah, it sounds effective. I'm just very careful of being circular here, because first of all, that's the observation. But I agree with you that once you see it, you say, and across multiple experiments, you're saying, okay, maybe it's adaptive. So maybe later the eye movements, as you develop in this task, they become more ballistic, also. So it's not only that they start earlier, but they also depart faster from the quadrant. So you can say you gradually shape this model, the spatial temporal model, that allows you to do, just very ballistic movement towards the predictable targets. And that sounds like something adaptive because it leaves you longer to cope with the unpredictable, right? So if you are getting rid of the predictable faster and you don't spend as much time there, so it gives you longer time to cope with the unpredictable, which is, I think, probably why we need to learn about regularities, right? I mean, we need to gain experience to cope with what we cannot predict, in a sense.
Yeah, interesting, really interesting. Okay, and last question. I'm not going. So, if anybody has a question, just raise your hand because I can, and we can also stop this because yeah, just last one, and then I'm going to close that. So I want to ask if you checked the misses, or if you examined, locations across the visual field. Let's say if the 0, 0 would be the center. I mean, would people be? I mean, I know you have these fixed locations, but let's say for the random ones, which are there differences between the ones that are? I assume people miss more the ones that are further away from the center, but is there a difference between the ones that are on the upper, lower part of the screen, right or left?
It is a task that allows free eye movement, so it is not designed well enough to look at this. Eventually, for a given target, n+2, your eyes could be here, here, or there.
Yeah.
But I think that in general, the spatial temporal statistics here can be addressed directly by controlling for eye movement. So there are some interesting works that have been done on the link between how long you wait for the search to appear and where the target will appear. So binding the timing of the onset of the search array and the likely location of a target. That's the work by Thewes and their lab. And so this is one way to look at it. Another way is to use a design like we are using, but in just smaller spatial region, and ask people to fix their eyes at the center. And then we can really look at also the learning of statistics of things that appear close to the center or far. Other than that, I have lots of interesting effects there, but because it's a highly dynamic task, so a lot of things are happening to spatial behavior in this continuous task.
Okay. Nir, thank you so much for joining us and for a really interesting talk. And yeah, have a lovely week. And we will meet again next week. I'm going to send the details. Actually, it's George Almeida from Portugal, but we will post all the information. So thank you so much. And
thank you. Thank you very much for coming.
You.
Thank you for being here.
Thank you.
Bye.
Bye-bye.